right, we just got done learning some of our basic derivative rules. We even discussed the derivative for sine and cosine. There's another derivative that will come up often in this class. It's the derivative for our exponential function e to the x. Now, I could just give you the rule, but before I just give you the rule, I want you to kind of show you where it comes from. Now, unfortunately, if we knew more of our derivative rules, like the derivative for our natural log, ln of x, or even implicit differentiation, which we will learn in our next unit, this proof might be a little bit easier. But for now, with the limited information that we have, if you will, rely on this definition of the number e with me, and that'll help us prove our new derivative for e to the x. Now, e is the number such that the limit as h approaches 0 of e to the h minus 1 over h equals 1. So this whole limit ends up equaling 1. So if we can use that definition of the number e, we're going to prove the derivative of e to the x. Now, let's go back to our long definition of derivative, our limit definition, where we can find the derivative of any function using the idea that the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x, right? And so I've plugged in my x plus delta x into our function e to the x. Now, some books, instead of using delta x, they use the variable h, right? It's just a distance. And instead of using delta x, I'm going to change it over here to h's instead. So the limit as h approaches 0 of e to the x plus h minus e to the x all over h. This is going to help us figure out the derivative of e to the x. Now, you'll notice that I have e to the x plus h. And if you remember from back in algebra, we have exponent rules, where if we have like bases and we're multiplying, we can simply add the exponents. Well, that rule can work in reverse. So if we were adding these exponents, I can actually separate that into two of the like bases of e. E to the x times e to the h is the same thing as e to the x plus h, right? So it's just that rule, but in reverse, okay? Now, you might notice that I have an e to the x in both terms. So I can factor out that common factor of e to the x. So now my problem looks like this. I have the limit as h approaches 0 of e to the x times e to the h minus 1 all over h. Now, this factor e to the x is not dependent on what h is. It doesn't matter what h is. There's no h in that factor, and so that's not changing. It's kind of like a constant. It's not a constant, but it's kind of like a constant. It won't change depending on what h equals, right? So because it's not a factor of h, or it does not depend on h, I can factor that out, and then that leaves me with the rest of the problem. The limit as h approaches 0 of e to the h minus 1 over h. Oh, does that look familiar? Wasn't that our definition of the number e? And so if we know that definition and we know what that limit equals, we can simplify this problem a little bit more. That whole limit, remember, equals 1. So really what we have is e to the x times 1, or just e to the x. So what we've just showed is that the derivative of e to the x happens to just be e to the x. So that's one of the easiest rules, derivative rules, to remember. The derivative of e to the x is always just going to be e to the x. What that's kind of saying is the slope of e to the x at any point ends up being the value of e to the x at that point. So the slope is the same as the y value, or the height of e to the x. Now this is kind of cool because this is the only function that ever happens to, where the slope is the same as its output value, the height or the y value. Kind of cool.